Hi! Within this lecture, we're gonna see special matrices starting with the identity matrix. So we have special terms for particular matrices, and one of them happens to be identity matrix. And what happens with the identity matrix is that if you multiply a matrix with an identity matrix, it gives you the exact same matrix. It's kind of a buffer, and nothing happens really. Okay, so consider this example. We have 2 by 2 matrix, and so 2, 3, 1, we multiply it with this matrix. Okay, we have ones diagonally over here, and it exactly gives the same result. If you do the multiplication on your own, pause the video, you're gonna see you end up with the same matrix. And the identity matrix can be 2 by 2, 3 by 3, 4 by 4. All you gotta do is just add ones over here. So we're gonna use this in quantum computations, okay? And all it matters is that you're gonna have ones diagonally over here. So if you multiply it with this one, okay, maybe you have done this the exact same thing by pausing the video, then it's great. You're gonna have 0 as a result, right? So if you continue to do this on your own, like 0, 2 with the 0, 1, you're gonna have 2 over here, and you're gonna have 3 at the left bottom side, and you're going to end up with the same exact matrix like you did in 1 minute ago. Okay, so this is called identity matrix. So if we want to create a matrix like 3 by 3, 4 by 4, don't forget about this ones diagonally over here, and you will be good to go. So over here we have 2 by 2, over here we have 3 by 3. It goes along with the same way as 4 by 4, 5 by 5, whatever that is. So we're gonna use this idea when we try to find like the inverse of a matrix. So for example, over here, if we have an inverse of a real number, you can write a to the power minus 1, and it's equal to 1 over a, right? You can just do this with 5 to the power minus 1, it's equal to 1 over 5. It goes along with the same way as 1 over 10 as well. So inverse of a matrix is if you multiply the matrix with its inverse, that will be equal to identity matrix. Okay, so it goes the same way as like a minus 1 multiplied by a, it's again equal to I. So how do we actually prove this? So if I come over here, you can see we have x and x inverse. Then I have, if I multiply this together, I have to get the identity matrix. If you do this multiplication by pausing the video, it will be a great exercise for you. So I really suggest you pause the video and do this calculation on your own right now. So if you did it, great. Now if you didn't do it, let me just do it with you. If you multiply 0 with this one, you're gonna get 1. Okay, if you continue, this will give you 0. You just write it over here. If you continue with the second row of the first matrix, and you will get 0 over here. If you continue with the second column, then you're gonna get 1. And this is exactly what we expected to see. Of course, you can create a formula with that logic over here with A, B, C, and D, and you can try to calculate what will be the inverse of a matrix, or you can just use online tools to understand the inverse of a matrix as well. So there is another term we should actually know about, which is called transpose. So this is exactly like transposing an Excel sheet. Maybe you have done that before. You're gonna have to switch the rows to columns and columns to rows. So if you take the 02 over here and write it over there, and if you take the 31 over here and write it over there, you're gonna have the transpose. It goes the same way if you do it with the 3 by 3. And the trick over here is that if you draw a diagonal over here, like a line over here, then you're gonna have to switch these things. Okay, switch these things and switch these two numbers over there. Then you're gonna have the transpose of that matrix. So more often than not, we're going to need this. Okay, you can do this with the first method that we have learned, or the second method is actually much more easier. You just draw a line and just switch the numbers across that diagonal. We're gonna use this again more often than not actually with the complex conjugates and the transposes themselves, because we're going to need this kind of information when we deal with the computation of quantum mechanics. For example, if you just try to get a transpose of these two matrices together, then it's equal to y transpose and x transpose multiplied. But again, as you can see, the ordering has been changed. So xy with transpose is equal to y transpose x transpose. Okay, so you can try to do, and you can try to actually prove this on your own as well as an exercise if you want to. You may just want to pause the video and try to do this on your own. You're gonna see this is actually equal to y transpose multiplied by x transpose. So this is again something that we should keep in mind as well. So another thing that we have to consider is the complex conjugate of a matrix. And again, complex conjugate is only changing the sign of the imaginary part of a complex number. So if we don't have a complex number over here, then it doesn't matter. You don't have to do anything with the real numbers. For example, over here, I have changed the sign of the complex numbers or imaginary numbers, that I didn't even change the real number 3, right? Complex conjugate is shown with a star like this, and the reason why we're doing is that we have something called adjoint, which is shown by the dagger sign or plus sign, and it means that you're gonna have to take the transpose of a matrix and then complex conjugate of that matrix. Again, this is called adjoint of a matrix. It happens that we're going to use this often again in quantum computations. So over here you can see a plus sign or a dagger sign. Again, it means that you're gonna have to take the transpose. Beware that we're taking the transpose over here, then just take the complex conjugate. And in fact, it really doesn't matter in which order you do this job. You can first take the transpose of it and then take the complex conjugate of it, or you can take the complex conjugate of it and then you can take the transpose of it. Okay? So beware over here, I just drew a diagonal and I switched the 3 and I with each other, and then I changed I to be minus I because I'm taking the complex conjugate of it, and then I changed the sign of this two together in order to find the adjoint of that matrix. So if you see X or A or any matrix with a dagger sign, it means that either you're gonna take the transpose and then complex conjugate, or you're gonna take the complex conjugate and then you're gonna take the transpose of it. Okay, hence the final line over here. So I know that's a lot of terms. Maybe you even forgot about the previous lectures and you don't even remember the terms complex conjugate. Maybe you will forget about adjoint in 10 minutes. But again, if you understood what's going on, then it's all gonna come back to you when the time comes. Don't worry about it. If you didn't understand, I really suggest you pause the video and just go back and watch it again. But if you understood it, there's no need to memorize it right now. It's all gonna make sense when you see it.